Hey everybody, welcome to week 3. This week we're going to be discussing Turing Computation. This represented a massive advance and, in some sense, the birth of modern theoretical computer science. So, very interesting stuff. It was developed by a very interesting guy, Alan Turing, and so I'm hoping that you all enjoy this week's material. Okay, so without further ado, let's get into it. So this week I'm experimenting a little bit with handwritten notes. I think this is it's a little more organic and it lets me draw pictures and things like that more easily. So let me know if you like this format. It can always be changed back to the standard LaTeX version if people find it distracting, but I mean, I kind of like it. So here's what we'll be discussing this week, just as a kind of outline. Firstly, we'll be recapping some of the themes from last week and providing some motivation for what we're trying to do with Turing Computation, which is to come up with a mathematically precise notion of computation that we can, theorize about more concretely. Section 2, I'll then talk a little bit how we define Turing computation and Turing computability. 3, I'll give you some examples. 4, I'll talk about how we encode certain problems that don't appear to be about Turing computations into a form that a Turing computer can operate on. 5, we'll talk about universal Turing machines. These are a very interesting kind of machine that allows Turing machines to be very flexible. And then we'll consider some philosophical questions about Turing computation, but mostly looking forward to things we'll discuss in future weeks. Okay, so recall from last week that we discussed some historical uses of computation, some kinds of algorithms that had arisen historically. And we noted a few themes, but 2 of those themes were the following. Okay, so firstly, we clearly have some notion of unambiguous instructions and effective procedure, right? There are those algorithms, say Eratosthenes' sieve, that are fully precise, and then there are other kinds of instructions. Say if I go and ask you to ask your best friend halfway through the computation as an essential step of the computation, that's going to be an unprecise kind of procedure, right? Non-precise kind of procedure. So we clearly have some notion of unambiguous instructions and effective procedure, but how do we make this mathematically precise? That was one of the themes we had. And the second theme that we saw is we want computers to be flexible. So maybe I can design a computer that does the sieve method for listing the number of listing all the primes under a certain number, but I want my computer to be able to do other stuff as well. I don't want just one computer to be able to do that and a different computer to be able to, say, play my YouTube videos or whatever. I want one computer to be able to do many things. And Turing computation, via answering theme 1, actually came up with an answer to theme 2 as well, as we'll see in the context of this talk. Now, as I said, Turing computability makes a start on both these issues, and as we'll see a bit in this lecture and we'll solidify in later weeks, it does pretty well. But what was Turing trying to do? Well, initially he had the idea of trying to think about what a human computer could do if they just followed rules to the letter, didn't run out of interest or concentration, and followed some fixed rules and had no restrictions on the time or the space in which they did their calculation. So this is him speaking in his seminal Computing, Machinery and Intelligence. Interestingly, in the journal Mind, so this is written in a philosophy journal. Wasn't just a computer scientist. Turing also did a lot of philosophical work. He writes, "The idea behind digital computers may be explained by saying that these machines are intended to carry out any operations which could be done by a human computer. The human computer is supposed to be following fixed rules. He also has an unlimited supply of paper on which he does his calculations." Okay, so how did Turing define what a computer was and what a computation involved? Okay, so he starts off with this definition of what a Turing machine is, right? So a Turing machine is a particular kind of idealized machine, and it consists of, firstly, so here, an infinite two-dimensional tape divided into cells. So that's what we have up here. We have this two-dimensional tape. It's infinite in both directions, and it's divided into these cells, right? Individual cells. And each of these cells can either contain a blank, which will either represent by a blank or sometimes a 0, or a stroke, which will sometimes represent as a 1. Okay? So there's a big long tape just covered in 0s and 1s. That's how you can think of it. And then there's a head, which I've represented as this funny character here, that looks at a particular cell. It can read what's in the cell, and it does one of the following 5 operations. Okay? It can either erase what's in whatever's in the cell. So this could be, printer or write a naught. It can print a 1 over whatever's in the scan cell. So, if there's a naught there, it'll get rid of the naught and add a 1. And if there's a 1 there, it just leaves the 1 as it is. It can move 1 square right, 1 square left, or it can halt. These are the 5 things that it can do. Okay? So the head can read what's in the square, and it can perform an action according to what's in the square. Okay? And the final component of the Turing machine is that there's a finite list of states that whenever you read a naught or a 1, you say what action should be performed and say what the next state is. Okay? So that could be, if you're reading a 1, print a naught, and go to state 5, whatever state 5 says. Okay? Good. So here's an example of a sort of silly kind of Turing machine I've done up in the top right of the slides. So state 1 says, let's assume this is the state that our little computer critter starts in. If you see a 1, print a 1 and go to state 2. If not, halt. Okay, so this computer critter, well, it's seeing a 1, so it leaves that 1 as it is or prints over the top, right? And then it goes into state 2. Okay, now it's in state 2, and it says if 1, move right and go to state 2. If not, print 1 and go to state 1. Well, it's seeing a 1, so it's going to go right. Now our little critter will be here in this cell, and it's going to go into state 2. So it's already in state 2, so it stays there. Okay. Sees a naught, and it prints a 1, right? And then it goes to state 1. So we're now back in state 1. Okay. It's seeing a 1, so it leaves the 1 there, and it goes back into state 2. And once it's in state 2, it can see a 1, and so it's going to move right and go into state 2. And we continue on like this. This is not going to compute anything interesting, but it gives you the rough idea of how a Turing machine works. Good. So with this definition in hand, how are we going to represent Turing machines? So there are a variety of things we could pick to do here. So one is we could have a table, right? So what does this table say? Well, it says that state 1, this is our state here. So our state 1, which will represent by Q1, this is the state we're talking about. This tells us that if you're reading a 0, I want you to print a 1 and go to state 1. If you're reading a 1, I want you to go left and go to state 2. Right? And then state 2, again, this is the instructions. If you're reading a 0, print a 1 and go to 2, or left and go to 3. We can also represent Turing machines by flowcharts. Okay, so this is exactly the same set of instructions, but we start in this is state 1. This tells us if you're reading a 0, write a 1 and go into state 1. If you're reading a 1, go left and go to state 2, and similarly. We can also represent Turing machines as a set of quadruples. So this is just a list, as it were, of the states, what they're reading, and then what their actions will be. So again, we're in state 1. We're reading a 0. We're going to write a 1 and go to state 1. We're in state 1. We're reading a 1. We move left and go to state 2. So these are 3 representations of the same Turing machine. Now, what does this Turing machine do? I give you a second's pause here, so you can pause the video if you want and try and work it out. What is this Turing machine going to do? We'll go through it. Good. So let's walk through it. Our Turing machine is in initially state 1, and it sees a 0, right? And so it's going to write a 1 and stay in state 1. It's now reading a 1, so it's going to move left, right? It moves 1 left, and now it's here. And now it's going to go into state 2, right, over here. It's reading a 0, so it's going to write a 1 and go back into state 2, right? And now it's reading a 1, so it's going to move left again. And now it's going to be in state 3. Now it's reading a 0, so it's going to print a 1. And now it has no more instructions if there are a 1, so it's going to halt. So this absolutely fascinating Turing machine will just print you 3 strokes on a blank sheet of paper. Now let's consider a slightly less trivial example. So here's a Turing machine that will add 2 numbers in tally notation. So in this context, we're adding the first number in tally notation 3, and we're adding it to 4. Now, what does this Turing machine do? So it starts in state 1, and if it's reading a 1, it deletes it and writes a 0. Okay, or a blank. If it's reading, it'll then go back into state 1, and if it's reading a 0, it moves right and goes into state 2. Then if it's in state 2 and it's reading a 1, it goes right. It's reading a 1 again, then it's back in state 2, so it goes right again. If it's reading a 0, once it's reading a 0, it writes a 1 and goes into state 3. If it's in state 3, it goes left as long as it's reading a 1, and then once it sees a 0, it goes right, so it's back here, goes into state 4, and halts. So state 4, a state with no arrows coming off it, as we've got here. This is what we call a halting state. This is the state it moves into when it halts and it has no further instructions. So the way that this Turing machine adds a number in tally notation is it just deletes the left one. It goes to the gap separating the two inputs, puts in a 1, moves to the left of the input, and moves onto the first digit of the output and halts. Often we insist that the Turing machine finish, or usually we insist that the Turing machine halt on the leftmost one of the outputs so that you can read exactly where the output is. Now, these Turing machines can get pretty complicated pretty quickly. So here's an example. You can find it on page 30 of Burgess, Boulos and Jeffries. We won't go through it in detail, but this is how to multiply two numbers in tally notation. I'll just describe roughly what this machine does. I'm not going to actually go through it because obviously we'll be here all day. So what this machine does is it starts off by deleting the rightmost one. So this is, we want to multiply here 2 by 3. So I've just deleted the first one here. And we'll call this the counter group, and we're going to call this is going to be the counter group, and this is going to be the leapfrog group. So once it's done that, it moves into this leapfrog routine here, right, in this part of the diagram here. And what that leapfrog routine is going to do is it's going to take these bits here, and it's going to move them over here, right? And then once the leapfrog is done, so this is here, it sends the Turing machine back to the counter group and gets it to delete another 1. So I'll change this back to a 0. And then the way this works is once it's deleted all of the counter group, it then moves to spaces right and then fills in 1s until it hits the leapfrog group, right? So there we did 2 times 3, and then it'll obviously move back to the right, the left-handmost one of the output and halt. So there we had 2 times 3, and we end up with 6 strokes. If I'd had 3 times 3, for instance, we'd have conducted the leapfrog another time. We'd have moved our leapfrog group out to here, and then we'd have filled in 1s all the way up to that leapfrog group, and we'd have got 9. So this is a simple-ish idea, but you can already see that this Turing machine is getting quite complicated. Okay, this is in terms of the kind of logical structure of what you have to do to affect these kinds of behaviors, it starts to get pretty intricate pretty quickly. Right, so we have these Turing machines. We've seen that they are good at crunching numbers, and we'll say that a problem is Turing computable, just in case for any instances of the problems there is a Turing machine that computes the solution. So this is the definition for Turing of what it is to be Turing computable, is to just have a Turing machine that computes the relevant problem. Thanks to Moritz Muller for the following example, we've seen that what we might think is that lots of problems aren't in fact about numbers. We've seen that Turing machines can crunch numbers, we can do multiplication. Of course, you can generalize to various other kinds of arithmetic properties. or arithmetical operations, but lots of problems aren't about numbers. Okay, so here's a problem called connected, and its instances of the problem are: I'm given an arbitrary finite graph G, right? So G is just some vertices with some edges between them, and I want to know if is G connected. So can I get from any node to any other node via some path? So for instance, this little critter here is not connected. Is connected because I can get to any point from any other path. Whereas this dude here is this is not connected because I can't get from this left hand pair to this right hand pair. Okay, but these are graphs, right? These are vertices and edges. These aren't, how do I feed this into a Turing machine, right? And the answer is, well, I can encode it as a problem about numbers. Okay. So we'll think about the graph, which is some vertices and some edges, as just, it's got n many vertices. So we'll think of these as just 1, 2, 3, 4, 5, up all the way up to n. And we'll denote this set by n in square brackets. So you can now consider the adjacency matrix. Okay, what is this? Well, it's just the function that takes in two natural numbers and it outputs 1 if and only if that pair is in an edge. So if there is an edge from I to j, and otherwise it outputs 0. Okay. So now look what we've got. We've got a function on two numbers that outputs a 1 or a 0. Okay. Now you can then write this adjacency matrix in this form. So you code the graph as this particular sequence given by this particular rule here. You can check that if you want. But the point is that what we can do now is, by considering this sequence that we get out of this function on numbers, we can consider whether there's a Turing machine, so some machine that when, if this is our tape, I feed it the code of some graph G coded up in this way, and it will give me, it will tell me whether or not this graph is connected. So this is now a problem about numbers, about the kinds of inputs we can have on Turing machine, and we have coded a problem about non-numbery things, vertices and edges, as a problem about functions on numbers that may or may not be computable. So this kind of idea of encoding is really ubiquitous across mathematical logic, and probably mathematics in general. But it's very, very interesting for dealing with issues like the Enchants Problem. Okay, so what was this problem? Remember, it's an arbitrary formula of first order logic phi, and we ask, is phi provable using the axioms of first order logic? So is there a particular sequence of symbols I can write out that will give me phi just from the axioms following the rules of inference? So again, this isn't on the face of it about numbers, right? These are about formulas. Formulas are the abstract types of things that I write down on paper, right? These are not obviously numbers in any sense, okay? But, well, what is a well-formed formula? Well, it's a sequence of symbols obeying certain rules, okay? So here's an axiom of first order logic I've written down for you. So it's not the case that there is an x such, well, x1, such that x1 is not self-identical, okay? Or, in the more common version, for everything is self-identical, okay? So what is this? I mean, it's a sequence of symbols, right? It goes not symbol, existential symbol, x1 symbol, not symbol, x1 symbol, equals symbol, x1 symbol. Okay, it's a sequence of symbols formed in accordance with some given rules. So we have some finite sequence of numbers, and what we can do, and this was Gödel's incredible insight, is that we can encode syntactic properties into, or syntactic objects into, the natural numbers. Okay, so for example, what we can do is we just assign, in a sort of slightly fiddly way, symbols, numbers to each symbol, right? So here we have our scheme for doing it here, right? So we take left bracket and assign it to 1. We take right bracket and assign it to 3. Comma to separate argument places, for instance, in many place predicates or functions, assign it to 5, not to 7, or to 9, existential to 11, and equality to 13. And then once you get to your variables, right, so xi is represented by 2 times 5 to the I. N place predicates, you want countably many of them. You want to always have a stock of an infinite stock of predicates, so you do it as 2 squared times 3 to the n times 5 to the I, and then the same for function symbols, right? You can then use prime decomposition, and that's one reason we have primes in here, for instance, to ensure that each formula, and indeed any sequence of symbols, it won't just be formulas, it can be any old, garbage like existential, left parenthesis, not equals. This will still get a code, but you get a unique code for each sequence of symbols, and in particular each formula, right? So, for instance, it's not the case that there is an x1 that's not self-identical. This will be coded by the following number using the prime decomposition, right? This number is going to be really big. These Gödel codes get massive very quickly, but these are still things that you can compute, and we can turn a problem about syntax and syntactic objects that it's not clear how to feed them into a Turing machine into problems about numbers. Good, so we've now got this notion of coding. We defined the Gödel code of phi, which we'll write with these corner quotes. In general, corner quotes around things denote the code of that thing. So earlier we had the code of G, for instance, written as G. It was a very different coding, but it was an encoding of something nonetheless. And we'll let context determine exactly what coding we're using. And mostly we'll be interested of encodings of formulas, right? Now, just a note here, since you can think of proofs as sequences, you can also code them too. So for instance, let's consider some sentence. We've got this kind of derivation. We have some sentence phi. We then say phi implies psi. And then from that, we infer psi via modus ponens, right? If I have, for instance, a symbol for end of line, which you can add should you want to. I'm going to represent it by these double commas. There are clever ways you can dispense with it, but let's just work with it for now. I can then represent this proof, right, as a sequence, right? It's phi, end of line, phi arrows psi, end of line, psi, right? We can code this up using a similar scheme as we had before, and we can talk about what proofs are as well, in terms of we can encode proofs into numbers, right? So now we can rephrase the Entscheidungsproblem, okay? we have these codes for particular formulas phi, and we say, well, instead of saying, I've got this formula phi, and I want to know if it's provable, how do I check whether that is provable? You're using a Turing machine when the input isn't even of the right form. You say, is there a Turing machine that when it's fed the code of phi, so this is just some natural number that we might represent in either tally or binary notation, and it tells me if phi is provable, right? Now, remembering that we can encode proofs as well. I mean, one thing you might do is you might try and have a particular Turing machine, take input phi. So it takes as an input the code of phi, and then it just starts looking for proofs in this mechanical way for phi. Just starts churning out possible proofs of phi, tries to find them. Okay. Now, as we'll see in future weeks, there is no such Turing machine. Okay, we'll see that shortly. But here's how you can make the problem fit into the mold of Turing machines and talking about formula codes. Okay, so we're now at a point where we've talked about what a Turing machine is. We've talked about how we can encode problems into things that might be attacked by a Turing machine. And we've talked about what it is to be Turing computable, namely to have a Turing machine computing the relevant function or problem or answers to the problem. Okay. So here's a question for you. If I tell you that your cell phone in your pocket is abstractly similar to a Turing machine, it's not exactly similar, but it's in an abstract sense similar. There's a question here. So far, I've just presented different machines for computing different particular problems. So we looked at the tally machine for addition, the tally machine for multiplication. So why don't you have separate devices, separate Turing machines? You have one Turing machine in your pocket. Why don't you have separate ones, each for sending texts, making phone calls, writing your lecture notes, looking up dog rescue videos on YouTube, all the good stuff that we like to do with modern computing devices? Why don't you have separate devices for these? And in fact, it's even more difficult, right? Because what we could have is, it's not just that you have one device that can perform lots of functions, but also I could write some instructions if I had suitable expertise, send them to your phone, or you install them on your phone, and then you can run new things that your phone didn't previously have on it by downloading the relevant app, let's say. So how is this possible? Why don't we need hundreds of different devices for doing different tasks? Now, here's where encoding gets really useful. Okay, so remember, if I can think of something as some sort of finite sequence, right? Often I can code it up by a number, and once it's in the form of a natural number, I can think about how to stick it into particular kinds of Turing machine. Now, is there anything else we've seen in this lecture so far that can be thought of as a finite sequence? So have a bit of a think, pause the video, and then go and look at the next slide. So as it turns out, the answer is yes, there are Turing machines. Turing machines are finite sequences of instructions, and the tape configuration themselves are also finite. So we can code up Turing machines and tapes configurations by numbers. Okay. So here's one coding scheme. There are lots of coding schemes and they're useful for different things, but this will give you the rough idea. Okay, so we let state I be coded by I, whatever that might be. So state 1 is coded by 1, right? State 24 is coded by 24. Let 0 be coded by 1 and 1 be coded by 2. This is a bit annoying, but it's just to avoid some peculiarities associated with 0. So that can be either read 1 or write 1. Later we'll use quadruples down here. And so it won't matter whether we distinguish between reading and writing. The position that the number occurs in will tell us exactly whether it's a read or write instruction. So we don't need to make a distinction between reading 1, writing 1, for instance, or reading 0 and writing 0. We'll then code left by 3 and right by 4. And then we can code up a Turing machine. So here's a list of quadruples in the quadruple format. And this, if you want to check it, this codes up the constant 1 function. Okay. Now, you'll notice that the first 2 components each time are entirely redundant, right? Because we do the same thing each time. So we say state 1 if you're reading a 0, do this. State 1 if you're reading a 1, do that. State 2 if you're reading a 0, do this. State 2 if you're reading a 1, do that. State 3 if you're reading a 0. So this is entirely repetitive. So we can just, we don't need to include that information, and you can just code up the quadruples in terms of 2 instructions, namely, a tuple of 2 instructions each time. Okay, so write, go to state 3, 0, go to state 2, write, go to state 1. Right, these are just the second components of this quadruple. Right. Okay, and now we stick that into our coding scheme. Right, so write is coded by 4, so we have 4, and then we go to state 3, so we have 3. 0 is coded by 1, and then we go to state 2, so there's 2 there. Write is coded by 4, and then we go to state 1, and so on, right? And then if you want to make this unique, you use prime decomposition, exactly as we did with the formulae, and you get, for each Turing machine, a unique natural number. Now, we won't directly need this here, but it's also useful to mention, especially for some other applications, that tape contents can also be coded. These are also finite sequence, or we can also code these as finite sequences via what's called the Wong coding. So a pair of numbers code what's to the left of the scan square, so we can also identify the scan square in binary, right? And B, the binary numeral of what's in the scan square and to its right. Now, we'll do this backwards, and it's because we want the units to be modified each time the tape is modified instead of one of the higher base digits. Okay, so look, here's a particular tape. So we have the machine head reading this square here. And so to the left of, or this tape, assume it's blank everywhere else, this tape will be coded as the pair of 1, 1, 1, 0, 1. That's what's to the left. And reading backwards from the right, because we want, if the machine does anything to affect the units of this binary numeral, it'll be 1, 0, 1, 1, 1. Okay, this is the pair of 29, 23, which you can code up in turn. So tape contents themselves are also the kind of thing that we can code up as numbers and then in turn feed to a Turing machine. Okay, so how can your smartphone do all that good stuff? Well, the answer is that it is abstractly similar to something called a universal Turing machine. Now, we won't go through the exact details of why these exist. You can check out the Burgess, Boulos and Jeffries problem 4.5 or section 8.2 if you want to get into it. But here's the idea, right? we've shown that we can code up machines as numbers, and we've shown how we can, say, code up particular problems that we might want to give to certain machines. So what we can have is a machine U that is able to run machines. It eats machine codes and inputs for those machines. So it takes in the code of some machine M, and it will run M, or it will simulate what M would do on X. Okay, input X. So here's a super buff Turing machine that can do absolutely any computation, provided it's coded up the right way, and it's got a bunch of bits coding up some Turing machine M. It's got some input X for M, and when you feed it this code, it will run M on X. Right? So it's the ability to code up machines as numbers and then have another machine act on those numbers that enables computers to be so flexible. There are computers that compute what other computers would do, right? So I could also change, if I wanted U to do something different from M, I could feed it some other code M prime for a different Turing computer, feed it an input for that M prime, call it X prime, completely different machine, completely different input, and it will still mimic the running of M prime on X prime this time. So there we have Turing computers, incredibly flexible, able to do any computation that is, there is a single computer that enables you to do any computation done by another Turing machine. Now, just before I close, I want to ask a few philosophical questions about Turing computation. And some of these will get answered in future weeks, but it's useful to consider some questions one might have at this stage and how these are going to be mathematically implemented later. Okay, so first question, are Turing machines too weak? I mean, all I've said is that, okay, all they can do is erase, move to different states, move left, move right. This is a very limited conception of what computation is. You know, why am I restricting at this stage to one tape, right? We've got one tape and we've got one head, right, that reads and moves around. But I could have, I could imagine multiple tapes, right? And I could have these Turing computers. So each one of these is a Turing computer that hooked up with wires so they can communicate to one another, and they can do computations in parallel, let's say. Does this give me a stronger kind of computation? Similarly, why not registers? Why am I restricted to only binary notation here? For instance, I could instead have a picture where I have, numbers in particular, registers, and I could have different operations on these. We'll explore this in a future week, for instance. So I could have, for instance, a notion where I have 28 in there and 5, and I move all the elements of this register across to get move to a case where I have none over here and 33 over here, right? For instance. So this could be another kind of computation that isn't so limited, perhaps, right? Maybe you can think of your own suggestions for other notions of computation that seem broader than Turing computation. And as we'll see in a future week, it turns out that Turing machines are really, really powerful, and they can simulate all these kinds of computation. Okay, so we'll see that as a bit of a spoiler. We'll see that in future weeks, but there is at least this kind of open question initially as to whether Turing computation gets us all the computations, or it's too weak somehow. So question 2, in a slightly different direction, maybe you think Turing machines are way too strong in a different respect. So there are absolutely no time constraints or space constraints on what a Turing computer can do. So let's suppose we set up some abstract Turing machine, right? And we want it to compute a problem, and we set it off running, right? And we wait, and we wait, and we wait. And then, the universe has completely gone cold. Everything, we've experienced the complete heat death of the universe. Perhaps some other large cosmological events have gone on, and we're still waiting. This abstract Turing machine is still running away. And then finally, yes, it calculates the answer and returns a 1 and halts, says yes to our problem. That still counts as a successful computation, despite the fact that the universe has, none of us are around to see it. Plausibly, if you actually tried to implement a Turing computer in this kind of situation, it wouldn't be able to, the mechanism wouldn't be able to survive that kind of radical change in the physical environment, right? So the question here as to what do we really mean by computable, and I've highlighted computable here, right? This isn't a mistake because there's some sort of modal idea here, right? What can be computed, right? That's what we mean by computable, right? Now, often we have a mathematical question here, so something entirely precise, right? So given some formally characterized class C, say this could be, as we looked at this week, Turing computable by a Turing machine. What problems are in C, or not in C as the case may be. So in that sense, we're mathematically perfectly clear on what we mean by computable, and Turing computation is now the sort of industry standard of what we mean by computable. Okay, so in that sense, that's a perfectly precise question, but there is a kind of underlying philosophical question lurking in the background here that's really tricky, which is, well, by computable, I sort of mean what can be computed. There's this modal element. So what are the relevant kind of modal considerations for us or our particular mathematics, right? Do we want to have some kind of time and space constraints or is that the more interesting notion of computation instead of this kind of computation that can go on for eons and eons? Okay, so it's a difficult question to attack. We'll see how we can come up with some mathematical ways of tackling this question in future weeks. And I think this is a case where we have a really nice kind of symbiosis between the mathematical questions, right, and the philosophical questions. By thinking about what we mean by can, what kind of possibility we are interested in, that then lets us think of particular kind of mathematical restrictions or expansions of what we mean or how we want to characterize particular computational classes. Okay, so one last philosophical question. So we saw that Turing machines can be really flexible via universal Turing machines. They can run lots of different programs on a single piece of hardware, a universal Turing machine. We've also seen that they can be, there's some sense, really strong. They can, run for a very long time and they have unlimited space. So a question that has popped up a lot in the philosophical literature and we'll analyze in future weeks. So might the human mind be equivalent to or modelable by, in some sense, a Turing machine? So can we mimic the human mind just using a Turing machine? So this is a fairly contentious question. It's difficult to see exactly what tools we might apply to attack this question, but we'll give it a crack in future weeks, and we'll see there's been some really interesting arguments put forward linking the mathematical results to these kind of philosophical questions. Okay, thanks for listening, and I'll catch my students in the seminar, and if you're just watching on YouTube, have a great day.